Okay, so let us now proceed to the wind load problem. As we can see here, we have a totally enclosed structure having a height from the ground up to the roof level of 3 meters. We have specified also the velocity came from the wind map 200 kilometers per hour with the wind direction. So the length that is perpendicular to the wind direction is what we call the width, or B. Okay, and then the opposite dimension, or the parallel dimension to the wind direction, is what we call the length, or the L. Okay, so here we are tasked to determine the pressure that is on the windward. So this is the windward side of the wall, and the opposite side of the wall, that is what we call the leeward wall. Okay, before we will proceed to the calculation, let us now have the formula here. P is just equal to, the pressure is equal to Q times GCP minus QH times GCPI. Q here is the QZ and QH that is set for windward wall, whether it is wall or roofing, whether it is windward or leeward. We have certain values for Q, employing the formula of QZ, this one. So this is the formula for QZ. We have also various variables here that we need to determine. Of course, the value of this one are present on the table set. This is found in the ASCE, or American Society of Civil Engineers, as well as adopted by NSCP locally. So G is the gas effect factor. For a rigid structure, we have 0.85, and then the pressure coefficient is present on the table, or in the figure 1-12 in the ASCE, 7-10. So we have a table for wall and a table for roof actually. And then for the GCPI, this is the internal pressure coefficient. We have also table, but if we have a fully enclosed building, it is set to be plus or minus 0.18. Okay, remember that before we can proceed to the pressure formula here, we need to determine the QZ, because QZ is equivalent to Qn as well as QH. So for the wall, Q is changing. Q has changing values according to the range of the height set in the table. Okay, so going back to the problem, first we need to convert the velocity, because on the formula of this QZ, V should be equivalent, or in terms of meter per second. So 200 kph here is being converted to meter per second. So applying the conversion factor, we have here 1 kilometer 1000 meter, and 1 hour is 3600. So if we multiply that and divide 200,000 divided by 3600, that is 55.55 meter per seconds. Okay, so we have already obtained this one. Next, the other factors. In this, we need to compute for the mean height, because in table 1-5 we need to determine the range of our mean height Z. So the mean height Z is the sum of 3 plus the half of the roof to the ridge distance. Okay, the roof to the ridge distance is half plus height 3. Okay, so this is the height 3 plus the dimension. This is multiplied by the 50%, or it is being half, to obtain a mean height z of 3.37. And basing from the table, 3.37 is somewhere at the lower range, 0 to 4.6. Then we have a factor of 0.85. Okay, so we now obtain the kz. Next is kzt. So it is being set to 1 for a flat terrain or ground. So we do not need to go over with the table. And then kd is also set for 1 for a loading that is not combined with any other loading, because we are just concerned with the wind load here in the problem. Okay, so it is just set for 1. Again, we do not need to go over with the table for that. So substituting all the values, we obtain 28.94 Newton per square meter. And then for the G value, for the gas effect factor, we have 0.85 for rigid structure. Again, we do not need to go over with the table. And then GCPI is plus minus 0.18 for fully enclosed building. So here's the table for that GCPI, or internal pressure coefficient. So here it is, fully enclosed building plus 0.18 or minus 0.18 for that. Okay, now for the pressure, we first proceed to the Windward Wall. This time we are going to refer to this figure 1-12. Again, this table is for the wall, and for the right portion, this is for the roof, because it includes angle here. So in this one, the criteria is L over B to come up with the CP, and for this one, H over L together with the angle to come up with the factor leeward angle. Okay, so anyway, we are just concerned with the walls here in the problem. So first we have the Windward Wall. L over B, all values are set to have a pressure coefficient of positive 0.8. So we do not need to compute for L over B for a while. Okay, so we just set CP is equal to 0.8. So this one. So substituting that one into the formula, as we notice here, QZ and Q is the same. 28.94 is the computed one, and then G is 0.85, CP is 0.8, and then plus or minus 0.18, then we will be having a plus sign. For the upper limit, we have 24.89 Newton per square meter. For the lower limit, we deduct this 5.21, we have 14.47 Newton per square meter. Okay, for leeward wall, so this time we need to compute for the L over B. So L, what is L? Again, L is the dimension that is parallel to the wind direction. This is L. And then for perpendicular dimension, that is B, L over B. And going back to our figure, L here is what? L here is 6 meters. B here is 7 meters. Is that correct? So L is 6 meters. This is B, or meaning we have 6 over 7. And 6 over 7 is 0.8. 86. Okay. So looking at the table, where is 0.86? From the leeward wall, 0.86 is 0 to 1. Then CP is set to be negative 0.5 for the leeward wall. And then we just have to substitute in this formula. So therefore, 28.94 times 0.85 times negative 0.5 is 12.3, negative 12.299 or 12.3 plus or minus 5.21. So if we have a minus sign, 12.3 minus 5.21, we have 17.51 as our limit. And then for the lower limit, we just have to do 12.3 plus 5.21. We have 7.09 or negative 7.09, meaning both are suction pressure. Okay, both are suction pressure. So that's it for the wind load problem.